Hello friends, welcome to the sixth video on complex integration. We are seeing the application of Cauchy residue theorem to evaluate real integrals. This video will introduce you to evaluation of type 2 integrals, which are going to be improper integrals of rational fractions. So rational functions. So we will see what are going to be the prerequisites for it. The Cauchy residue theorem, it says integral over C f of z dz is 2 pi I times summation of the residues. The evaluation of residue at simple pole given by limit z tending to a, z minus a into f of z. The multiple pole residue is given by limit z tending to a, 1 by n minus 1 factorial, d power n minus 1, dz power n minus 1 the derivative, z minus a power n into f of z. Now what we refer to as type 2 problem is going to be improper integrals of rational function. So what we are going to do over here is we are going to integrate a function from minus infinity to infinity. The function is going to be of the format f of x dx, where this f of x is going to take the format capital P of x divided by q of x. Both P of x and q of x are going to be functions, rational functions, and we are going to consider the case where the q of x, the denominator, has 2 more than the degree of p of x. So compared to the degree of your p of x, the degree of x must be 2 more than that. So if you have your degree of p of x to be equal to 1, so your degree of q of x must be 2 more than this. So 2 plus 1, it has to be 3, 4, 5, anything of that sort. So it has to be more than that of 3. If it is going to be lesser than that, then this methodology will not work for your application for Cauchy residue theorem. So keep in mind, we are going to integrate a fraction of the form p of x by q of x, where p of x has a degree which is going to be lesser than that of qx by 2 or more, and we make sure that q of x does not vanish for the real number. In type 1, what we consider as the boundary was our unit circle with center 0, 0 and radius 1 unit. But for this was for your type 1. So type 2 now takes the limit or the boundary as minus infinity to plus infinity. Hence what we consider over here is the axis that varies from minus real number part to a plus real number part, and the semicircle which is going to be available in the upper half of your real axis and not the lower half. So this is going to be the real part, upper part of the real axis that varies between minus r to r. So if my pole is going to lie in the upper part of my semicircle, the semicircle in the upper half, then we say that it is going to have a residue. When the pole lies in the lower part, then we say that it doesn't have a residue in that particular position. So keeping in mind the 2 points, p of x and q of x are going to be functions in a type that q has 2 more degree than that of x, p of x, and the validity of the residue is guaranteed for the poles that lie in the upper half of the real axis in the semicircular portion that is going to vary between minus r to r. So we will have these things in mind, and now move on to see how we can evaluate the integral from minus infinity to infinity x square dx divided by x square plus a square and x square into b square. Now we can see that p of x is going to be x square, which is going to be of degree 2. And what is our q of x? Q of x is x square plus a square and x square plus b square. So x square into x square, the largest of it will give me the degree of the expression to be equal to 4. So you can see that the difference between your p of x and q of x is going to be 2. So if it is 2 or more, then I can apply the type 2 integral. In which case, what I'll have to first do it, convert the function which is going to be a function of x between minus infinity to a function of z. So what will be the function of z? Wherever I have x, I will replace this x with z. So I have this as z square divided by z square plus a square into z square plus b square. Now our function is ready. We are going to apply the same process what we have done for the estimation of Cauchy residue theorem evaluation. So step 1, find the pole. Step 2, identify what is going to be the boundary. Step 3, find whether the poles lie inside the boundary or outside the boundary. Step 4, estimate the value of the residue at the poles. And step 5, 2 pi I times summation of the residues of f of z. So we move on with step 1. What is our step 1? Is to identify what are going to be the poles, which is got by equating the denominator to 0. The denominator as z square plus a square, z square plus b square equal to 0. When I equate z square plus a square to 0, z square will be equal to minus a square, z will be equal to plus or minus root over your ai. So this is going to be equal to minus a square. So z will be equal to plus or minus a times I. So I have got my first set of poles. What are going to be my second set of poles? Z square plus b square equal to 0. Z square equal to minus b square. Which implies z is equal to plus or minus root over minus b square. So z will be plus or minus square root of b square is b with a negative sign. So you have this as I. So totally how many pole? Power is 4. So we have 4 poles plus ai minus ai plus bi minus bi. Z plus ai into z minus ai, z plus bi, z minus bi. So this is going to be my factor when I am going to factorize z square plus a square into z square plus b square. So my step 1 is over. Now we move on to step 2. What is my step 2? Identifying the boundary. What is going to be my boundary in this case? It is going to be the upper half of your circle. So you have this to be equal to the semicircle, which varies from minus r to plus r. This is going to be your 0, your positive axis. And the other parts. Okay, now let us consider the poles, which is given by z is equal to ai, z equal to minus ai, z equal to bi, z equal to minus bi. Now this can be written as 0 plus ai because the real part is not here. This is 0 minus ai, this is 0 plus bi, and this is 0 minus bi. After identifying the boundary, step 3 is going to be the positioning of the poles in our given boundary. So what will be the x comma y coordinates for this? This is 0 comma a, 0 comma minus a, 0 comma b, 0 comma minus b. We will try plotting these 4 points 0 comma a, minus a, b and minus b. 0 comma a, 0 and a being a positive number, say suppose this is going to be my point 0 comma a. So this lies inside my semicircle above the real plane. 0 comma minus a, 0 minus a, this is going to be my point 0 comma minus a. So now this lies outside my semicircular region, which is going to be my integral part. Next 0 comma b, say b is going to be any positive number. So 0 comma b is going to lie also inside the semicircle above my real plane. And now 0 comma minus b will be something below it. So this lies outside it. So I see that out of the 4 poles, the two poles that lie inside are, so poles that lie inside are Z is equal to AI and Z is equal to BI. So the remaining two poles lie outside, and hence what do we know about the residue at poles that lie outside will be equal to 0. So my step 2 boundary over, step 3 identification of the poles inside the boundary is over. Now we move on to step 4. What is our step 4? Find the residue of the function at the poles. So totally how many poles? 4 poles. Of them 2 lies outside, and poles that lie inside is now to be considered. So out of it I am going to find residue at Z is equal to AI. So this is given by limit Z tending to AI. The formula Z minus AI into the function f of Z. Now we will try to rewrite our function f of Z. What is our function f of Z? F of Z is Z square divided by Z square plus A square, Z square plus B square. Now this can be rewritten as Z plus AI, Z minus AI, Z plus BI, product Z minus BI in terms of its poles. So now let me copy paste the function over here. So limit Z tending to AI, Z minus AI, Z square divided by Z plus AI, Z minus AI. Now this is not going to be affected, so I can keep it in the unexpanded form as Z square plus B square. Now minus AI cancels off, leaving you with limit Z tending to AI, Z square divided by Z plus AI into Z square plus B square. Now let me apply the limit over here. So it is AI the whole square divided by AI plus AI. Over here it is Z square, so AI the whole square plus B square. On expansion we have this to be equal to AI the whole square divided by, this is going to be AI plus AI, AI plus AI, AI the whole square plus B square. This is what we have. Let us simplify. A square, I square makes it as minus 1, AI plus AI makes it as 2 times AI. This is A square with I square to be minus 1 plus B square. So let me take a minus sign common outside from over here. So this will give me A square minus B square into 2AI. Minus sign can be cancelled off. One of the A can be cancelled off, leaving us with A divided by 2I into A square minus B square. This is my residue 1. So let me find out the second residue, which is going to be residue at the point Z is equal to BI. So it is limit Z tending to BI, Z minus BI into f of Z. Now here we replaced Z square plus A square as the product and kept this as such. But now since we are replacing for B, let me keep Z square plus A square as such and replace my B square alone in product of its poles. So this becomes limit Z tending to BI, Z minus BI, Z square divided by Z square plus A square, Z plus BI, Z minus BI. Now this can be cancelled off applying the limit we have bi the whole square by bi the whole square plus a square, and this is bi plus bi. So this makes it as minus b divided by minus b square plus a square, and this makes it as 2bi. So let me make this as minus b square divided by 2bi into a square minus b square. One of the b can be cancelled off, leaving us with minus b divided by 2i times a square minus b square. So this is going to be my residue 2. My residue 3 and residue 4 are going to be equal to residue 3 at z equal to minus ai is 0, and my residue 4 at z equal to minus bi is 0. So now we move on to the fifth stage, which is integral from minus infinity to infinity the function f of x dx, which is given by 2 pi I times summation of all the residues of my function f of z. So it is 2 pi I times the first residue, which added up to a divided by 2i into, it was a square minus b square, a square minus b square, plus what was the second residue, minus b divided by 2i into the quantity was a square minus b square, and the remaining two things were 0. So 2 pi I, let me club the denominator since they are the same. So 2i a square minus b square. So I have in the numerator a minus b. 2i and 2i can be cancelled off. This a square minus b square in the denominator can be rewritten as a plus b into a minus b. And now I have a numerator a minus b and a pi over here. A minus b can be cancelled off. Hence, what do I have finally as integral over x square divided by x square plus a square into x square plus b square between minus infinity to plus infinity, differential to be equal to, numerator is going to be pi and the denominator is going to be a plus b. So this evaluates the integrand of the form at px by qx, where your qx is at least 2 or more degree than that of your p of x. Thank you.